welcome back. We've got polynomial functions here. Remember, polynomials, okay, we talked about polynomials a long time ago, and if you remember, a polynomial is one term or the sum of two or more terms. That's what a polynomial is, okay? Examples of polynomials could be 3x, or 5x plus 2, or negative 6x to the fourth plus 3x cubed minus 6x squared plus 7. If I have one term, that's called a monomial. If I have two terms, it's called a binomial. In this particular case, I have four terms, so anything over three terms is called a n-term polynomial, where n equals the number of terms. So this would be a four-term polynomial. If I had three terms, it's called a trinomial. So those are polynomials. We should try to remember those facts. Now, polynomials by definition cannot have any negative variable exponents. And you cannot have any variables in the denominator. So if you have 5x to the negative third power, that is no longer a polynomial. That exists. It's not saying that you can't work with that. That's going to become 5 over x cubed, but it's not a polynomial. That's all we're saying. I can plug in a value for x there. I can use it to add fractions or multiply or divide. I can do a lot with that. But all we're saying is that it is not a polynomial. So if you have a negative exponent or a variable in the denominator, you do not have a polynomial. A constant is any real number, period. Any real number is a constant. So in this green example up here, the constant would be positive 7. Very good. Okay, very good. Also, about the constant, it is a number. It is not a variable. So the constant, degree of the constant will always be 0. Okay. Now, as far as the degree of a polynomial in one variable, that means that the polynomial consists of only variables x or y or z. One variable throughout and only one variable throughout. So the highest degree exponent, that is the degree of the polynomial. So when I have something like x to the fifth plus x squared minus 7, since x to the fifth is the variable with the highest exponent, and I'm only working with x's and constants, it's a one variable polynomial, and the degree of this polynomial would be 5. Does that make sense? Yes?
If you would put y in there, but y would equal like 2x, would that...
The question is, if you put y in there, but y equal 2x, would that still work? Yes. But you're not going to see that a lot, but the question is valid. If they have given you a y, if they have, for example, minus 7y, but then they tell you y equals 2x, well, then you would be able to substitute, and then this would become x to the fifth plus x squared minus 14x. That would be a polynomial, but only because they told you a substitution value for y. If they did not give you that information right here, this wouldn't even be a polynomial. There would be no degree because it is not a polynomial in one variable. Yes?
Now, if there were a y, it would be two variables.
If there was a y and this was not included, like I just finished saying, then it would not be a polynomial. Thank you. Okay, now, coefficient. Coefficient is the number being multiplied to a variable. Period. That's it. Coefficients are the numbers being multiplied to variables. Doesn't matter the degree of the variable it's being multiplied to. It is simply the coefficient is the number being multiplied to a variable. And the leading coefficient is the coefficient of the leading exponent. It's the coefficient of the term with the highest degree. Okay? It is the coefficient of the term with the highest degree. So, when we have a general polynomial, p of x, we have a0 times x to the n plus a1 x to the n minus 1 plus dot, 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 and et cetera, and it ends with a to the n. This guy right here, that's going to be the constant. There are no x's there. And this a right here, that's the leading coefficient. And the exponent of the leading coefficient is the largest exponent of the polynomial. That's going to determine the degree of the polynomial here. Make sense? Okay. Now, let's run through these right quick. I want you here, please, to tell me the degree, the leading coefficient, and the constant of each polynomial in one variable. If it is not a polynomial in one variable, explain why. So let's just go ahead and call lead coefficient degree A, lead coefficient B to make our lives easier, and constant C. So I've got A, B, and C. So what will my lead coefficient be here? Yes, sir? 7. Excellent. What would my... sorry. Why don't we pay attention? What is the degree? What is the lead coefficient? What is the constant? Awesome. Okay. What is the degree here? Not a one variable polynomial. Very good. So you can't work with that. What's the degree here? This is not a polynomial either because x is in the denominator. Very good. So this is not a polynomial. Very good. What's the degree here? 5. Very good. Even though it's not in order, that's the highest degreed exponent. What is the lead coefficient then? -1 because it belongs to the leading degree. Very good. And the constant here? 0. There is none. Very good. Excellent job. Okay. Now, when we're talking about evaluating, this is old school stuff already. This is Algebra 1. Evaluating just simply means plugging in, substituting. They're giving you some function. Remember, function notation, don't be scared of it. When you have f of x equals whatever, x plus 3. Remember, f of x is just a fancy way of saying y. Y is the independent. F of x is the independent. And this f here, that's just the name of the function. This is function f with independent variable x. That's it. If I have a g of w, okay, this is function g with independent variable w. K of t, this is function k with independent variable t. Does that make sense, guys? So don't be scared of function notation. We've gone over that already. All right? Now, let's go ahead and find f of 1 here. What do we got? 3 times 1 squared minus 3 times 1 plus 1 is going to be 3 minus 3 is 0 plus 1. Excellent. Okay, how about f of 2? 3 times 2 squared minus 3 times 2 plus 1. That is 12 minus 6 is 6 plus 1 is 7. Very good. And f of 3 here, what would that be?
19.
It's going to be 19. Very good. Okay, now, what would f of r be here if r was 12? Well, in this case, f of 12 is going to be 3 times 12 squared minus 3 times 12 plus 1. So that's going to be 144 times 3, which is going to be 432. Very good. Minus 36 plus 1. So I'm going to get 297 is exactly correct. Very good. 397. So you said 297. He did say 297. Yeah, that's what I thought. Thank you, sir. Thank you very much. Okay? Does that make sense? Awesome. Okay. Next. Now let's go ahead and jazz it up a little bit and let's replace the variable with other variables. If I want to find q of a squared and this function q of x, well, this is going to be a to the 6th plus 4a to the fourth minus 5a squared. Just for giggles, what's the degree?
6.
Give me 1 second, please. Excuse me, son? Okay, thank you. Okay, what is the degree here, please? 6. 6 is the degree. What is the lead coefficient? 1. What is the constant? Good. Okay, now let's do q of a plus 1 minus 2q of a. Okay, so what am I replacing the x with? Okay, so it's a plus 1 squared plus 3 times a plus 1 plus 4 minus 2 times the function q where I'm replacing x's with a's. So it's going to be a squared plus 3a plus 4. Now it's Mickey Mouse time. This is a squared plus 2a plus 1 plus 3a plus 3 plus 4 minus 2a squared minus 6a plus 4. Please be careful. Minus 8, sorry, thank you. Please be careful, not only with that, but with this part right here. A lot of times, people will subtract these two, and that is wrong. Okay, you cannot subtract these two because this 2 has to be distributed first. Okay, so now let's combine like terms. So what do I got? I got an a squared and a negative 2a squared, so that's negative a squared. I got 2a plus 3a is 5a minus 6a, so minus a. And then I got a 1 plus 3 is 4 plus 4 is 8 minus 8 is 0. Boom. And then you can factor this out and take out a negative a, and you have an a plus 1. Does that make sense? Okay, awesome. Now, let's check out some graphs of polynomial functions. Do you guys remember that paper that I gave you guys with all the families of functions? Okay, you should memorize that. And just in case you didn't, I went ahead and hooked you up with some of these. Okay? Thank you very much. What I want you to see is the following, guys. I have a bunch of different types of functions here, and function end behavior, how a graph is going to behave. Okay, it doesn't mean they're going to behave poorly or well, but how is it going to end? What's the end behavior of the graph? Is always going to be dictated by the power of the function. So here I've got f of x is equal to negative 3x plus 1. When I have a power of 1, that is a linear equation. Linear, correct?
Yes.
So it's linear. Now, just out of curiosity, what's the degree of the linear?
1.
Very good. Okay, this is a quadratic because it's x squared. See how this goes like this? Okay, what is the degree here? Okay, notice the end behavior. Notice the end behaviors here. This is an x cubed. So what's the degree here?
3.
Okay, notice how it's behaving. And when I'm talking about behaving, remember that we read graphs from left to right. Very good. Thank you, gentlemen. Awesome. Awesome. Now, this guy over here is x to the fourth. If you notice, you have, it's like a W, but look at the end behavior. Look at the end behavior when it's to the fourth power, and look at the end behavior when it's squared. Just hold on. Yes, sir. Okay, hold on. Don't tell me what you're noticing yet. Keep it to yourselves for 1 second. Thank you. I'm very proud of you, though. Let's look at this. I got x to the fifth power, right? Let's notice the end behavior here between x to the fifth and x to the third and x to the first. Let's just take a look at that, okay? And then we've got this guy right here, and this is x to the sixth, okay? Now, what do you notice about the squared, the fourth, the sixth? When they're all positive, remember, The a's here are positive. They are all even exponents. What do you notice about the end behavior? They're both ending up. They're, they're going up on the left and up on the right. Up on the left, up on the right. Up on the left, up on the right. Now, for the odd degrees, don't count this guy because this is an odd degree with a negative, so that switches a little bit. But what do you notice about the end behavior of the positive odd degrees? Yes, you're going down to up. You're going down to up. You guys seeing this?
Yes, sir.
Okay. Now, I get rid of this?
Yes, sir.
Okay, thank you, gentlemen. Okay, now, no big deal. No big deal. Just had a few windows open. Okay, now, graphs of constant functions. If you guys remember, graphs of constant functions, okay, are graphs that are going to be horizontal lines. This is an f of x equals c. That's a y equals a equation. Remember, the slope of this line is 0. Very good, okay? This is very good, very good. Well done. And it's the same y forever. What do you think the degree of a constant function is?
0.
0, because there are no variables. Very good job. Excellent. Does that make sense? You sure, my friends? Okay. Now, we're also going to be talking about increasing and decreasing parts of graphs, and I want to show you something. Okay? Look at what's happening here. As x is increasing, isn't y slowly but surely increasing as well?
Yes.
Okay, pay attention to that because you're going to need to know that. You're going to need to understand those mechanics. Let's look at a decreasing graph right quick. As, bless you, son, as x increases to infinity, what's happening to y? Slowly but surely. It's going down. So that is called a decreasing function. Okay? This is all review again. We've done this already. But I just wanted to just give you another visual before we continue today. Does that make sense, gentlemen? Okay, awesome. Good job. Okay, so notice that the shapes of the graphs for even degree polynomials and odd degree polynomial functions, we already did that. And you guys did a great job. Now, what I got to follow up with is letting you know that the degree and the leading coefficient of the polynomial function determine the graph's end behavior. Okay? The end behavior is determined by the degree and the leading coefficient. If it's positive, it's going to end one way. If it's negative, it's going to end another way. If it's odd, it's going to end one way. If they're even, it's going to end another way. All right? So, what is this man talking about? Well, first of all, remember that the domain values are x values. And this right here, x arrow to infinity, what this means, just so you can, again, just review the stuff that we've already learned before. X is increasing positively to infinity. So that means it's going further and further and further and further to the right, slowly but surely. Even on a parabola, even if it's really narrow, little by little, am I not going little by little further to the right, eventually? So that would be what I mean by x is increasing. As far as a decreasing, it would be represented as a negative infinity. And what would happen here is, okay, as x is increasing slowly but surely, correct? It's getting wider, right? Okay, good. Does that make sense? Hello? What's up, son? No. The x is increasing and the y is decreasing. The x is also decreasing to negative infinity this way. This way right here. Okay? So, well, it depends on how you look at it. Actually, I should have not done that one. Negative infinity, we're talking about this side. As this graph keeps going little by little, my x is getting smaller and smaller little by little, correct? Okay. So, now, let's go ahead and get rid of this. And let's talk about what we have to memorize. The end behavior of polynomial functions. Okay, first of all, if the degree is even, the leading coefficient is positive, the end behavior will be, the shortcut that I like to use is, I call it up and up. Up and up. Now, mathematically, what does that mean? All right, as x is going further and further to negative infinity, what's happening to the y values?
It's going slowly up.
They're increasing. So f of x increases to positive infinity as x goes to negative infinity. But what's happening on the other side of this? As x is increasing, what's happening to my y? It's also increasing. So as f of x, y values increase as the x values increase. So when I have an even function and I have a positive leading coefficient, I don't care if it's second power or 26th power. The end behavior will be up and up. Does that make sense, gentlemen? It's the exact opposite for when the leading coefficient is negative. It's the exact opposite. It's going to be down, down. Yes? Says f of x, as f of x is increasing to positive infinity as x is increasing to negative infinity, or decreasing to negative infinity. And f of x, which is y, is increasing to positive infinity as x is increasing to positive infinity. Now, the negative leading coefficient with an even degree. Okay? Now, in this case, I am ending with down and down. What's happening here? As x is going slowly and slowly negatively decreasing, the y values are also decreasing. And as the x values slowly and slowly increase, the y values also decrease. Yes?
So why can't you put negative infinity to positive infinity? And then you put...
You can't put negative infinity to positive infinity here because we read graphs from left to right, son. Left to right. So as x is going slowly and slowly to negative infinity, decreasing, my y values are decreasing. That's the left quadrant, son. Then, for this guy, as x values increase positively, y values are also decreasing. I'm going from left to right. What's the problem? Okay. So, if the degree is even, it's either up and up or down and down. If the lead coefficient is positive, it's up and up. If the lead coefficient is negative, it's down and down. Does that make sense? Okay. Awesome. Now, odd. Odd degrees. If the lead coefficient is positive, then I have down and up. Check out what's happening. Remember, we're going left to right. As x is decreasing here, okay, what's happening to the y values?
It's
Increasing. No, it is not. As my x values are going decreasing, what's happening to my y values? They're decreasing in the long run. As my x values are increasing, what's happening to my y values? Increasing. So I have down and up. Down and up. And it's the exact opposite, okay, the exact opposite for when it's odd and negative. If it's odd and negative, okay, going left to right again, as x is decreasing negatively, what's happening to the y? Hello? It's increasing. Very good. And as x is increasing infinitely, what's happening to the values of y? They're decreasing. So when it's odd degree negative, it's up and down. Yes?
Cut the graph by half.
I have no idea what you just said.
Cut the graph in half and read it individually.
I don't cut the graph in half and read individually. No. I look at the y-axis. From the y-axis, sir, there's the left side of the graph and there's the right side of the graph, sir. That's how I read it. Okay, the y-axis is your, I guess, cutting tool. It's the y-axis. Okay? Does that make sense, guys?
Yeah.
It's easy, right? Yeah, very good. Yeah, unfortunately, I can't leave it there because this is on video and you can go see it. And we have to practice now because we're done with actual knowledge. Now let's see if we can handle some practice problems. Now, what's going to happen here is I want you to describe for me, please, A, the end behavior. Determine whether it represents an odd degree or even degree, and state the number of real zeros. So for number one, what if I went like this? Hey, A, describe behavior, end behavior. Down, down. Okay, so basically, mathematically speaking, as x is decreasing, as x goes to negative infinity, what's happening to the y? Y is decreasing as well. And as x is increasing to positive infinity, what's happening to y? Y is decreasing also, making it a down and down. Yes? Okay, so it's down and down because we're talking about the end behavior, not each individual peak and valley. We're talking about the end behavior. Okay, so B. Is this going to be an odd or an even? It's going to be an even, absolutely. And you can even tell me what is the sign of the leading coefficient here. It's going to be negative. Very good. Very good. Very good. And last but not least, how many real zeros do I have here? Yeah, this guy and this guy. So I got 2. Does that make sense? Pretty simple, no? You sure?
I don't understand the real zero.
Okay. By saying you don't understand the real zeros, it honestly pierces my heart because we just finished a whole chapter on finding the real zeros. Guys, aren't the real zeros the x-intercepts? The x-intercepts, we have gone over this 100 times. Those are called the solutions, the roots, or the real zeros. So when you're telling me, y'all, that you don't know the real zeros, it's like a shock to my heart. Solutions, roots, real zeros. They're all the same. It's the x-intercept. It's the point which intersects the x-axis. Those are the solutions of functions. Yeah, man. We had talked about that. But thank you for asking again. I will heal in time. Okay. Does that make sense? Okay, so then let's do this. Let's do another one. Let's do another one. How about if I give you something like this? Okay? So what's my end behavior? Down and up. I'll just say it verbally this time. As x is decreasing, okay, y is decreasing. As x is increasing, y is increasing. What degree would this be? Odd or even? Odd. And would it be positive or negative? Positive. Very good. How many real zeros? One. Very good. Very good. Excellent. Let me split this up right quick and just do one more. Okay. What if I gave you this? Okay, so this is down and down. Now what's happening with down and down? Remember, as x is decreasing, y is decreasing. As x is increasing, y is decreasing. What is the degree, odd or even? Is it going to be positive or negative? Negative. And how many real zeros? None. Does that make sense? Okay, so homework is valid. Thank you very much. Have a great day. And thank you. Thank you too.